Hey everyone, welcome back to the Foundry by Forge College. Big congrats on finishing up the capstone assembly and knocking out that final case study. You've officially leveled up to the advanced Solana concepts track. Today, we're unpacking a really fascinating question. What exactly is proof of history? Let's get right into it. So think back for a second to our recent lesson on Turbine. We talked about chunking block data and blasting it across peers at just blistering speeds. But here's the massive catch. Coordinating all that high-speed, decentralized data without a single global clock? It's literally like trying to herd cats. I mean, if thousands of independent nodes are processing transactions at the exact same fraction of a second, how on earth do they mathematically agree on what happened first? Here's our blueprint for today's explainer. We'll look at the network time problem, define what proof of history actually is, use metronomes and film strips as a mental model, break down ordering versus consensus, and finally wrap up with high throughput in action. All right, section 1, the network time problem, or how we coordinate decentralized clocks. The basic issue here is that relying on standard wall clocks or network trust causes massive coordination delays, and that just slows everything to a total crawl. Which brings us to section 2, what is proof of history? Let's take a look at this cryptographic stopwatch. Okay, so proof of history, or POH. The technical definition is that it's a deterministic, verifiable sequence of cryptographic hashes encoding the passage of computational time. Wow, right? That is a highly technical mouthful, but here's the secret to actually understanding this. Proof of history is not a new consensus algorithm. Do not think of it as a replacement for validators voting on state. Instead, it's just a timestamping layer. It creates a verifiable internal clock for validators, mathematically proving that time passed between two events without anyone ever needing to look at an actual physical clock. So, how does a clock tick without any gears or springs? Well, in this hash accumulator, we start at the very beginning with a base hash. We'll call that H0. To generate the next step, H1, the validator hashes H0 along with our first piece of data. Then, to get H2, we hash H1 with our next piece of data, and so on, theoretically forever. Because each step sequentially depends on the precise mathematical output of the step right before it, it enforces an unbroken, provable order. You literally cannot skip ahead. There's no way to calculate H2 without knowing H1 first. Now, the absolutely crucial point here is that hash functions are one-way and collision-resistant. If you've taken some of our other foundational tracks here at Forge College, you probably remember that computing a cryptographic hash takes a defined, predictable amount of time. But verifying it? That's incredibly fast and cheap. And because the math is strictly one way, no malicious actor can fake or reverse engineer the sequence. It's totally secure, and it proves beyond a shadow of a doubt that computational time had to elapse to generate that exact sequence. Moving on to section 3, metronomes and film strips. This is a mental model to help visualize things. To build this mental model, I want you to imagine a metronome ticking away at a steady, perfectly consistent pace. That represents our continuous sequential hashing process in Solana. Tick, 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 hash, 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 right? Now, imagine a physical movie film strip. That film strip represents the record of external events, like your transactions, where every single frame embeds a cryptographic fingerprint of the frame right before it. Think of proof of history as the precise numbering system printed right on the edge of that film reel. I actually love this movie analogy. Just imagine you're watching a crazy action movie, and the projectionist drops the reel, scattering the frames everywhere. You wouldn't need a clock to know the car chase happened before the explosion, right? You just look at the sequential frame numbers to piece it back together. In Solana, proof of history tells us exactly when a transaction happened relative to another. It embeds transactions directly into the timeline, almost like a camera operator leaving a sticky note on a specific movie frame. If that note is on frame 100, everyone who later inspects the strip guarantees it occurred after frame 90 and before frame 101. It's just beautiful, deterministic ordering. All right, section 4, ordering versus consensus. These are two very different jobs. It is so critical not to mix these concepts up. A standard wall clock or network time protocol proves absolute time for scheduling. Proof of history, on the other hand, proves order and elapsed computation. That's our numbering on the film reel we just talked about. And finally, consensus is about agreement on the state and fork resolution. Let me say that one more time just to be completely clear. POH just provides the ordering signal. Consensus mechanisms, like leader election and voting, are what actually lock in the final state of the blockchain. They are distinct, complementary jobs. And finally, section 5, high throughput in action. Let's look at how this cuts coordination costs. Let's compare the real-world metrics here. We're looking at time to commit, which is the speed at which a validator can assemble a candidate block, against verification cost, which is the computational heavy lifting required by the network to confirm that order. Proof of history drastically reduces both of these massive bottlenecks. Because the cryptographic timeline is already baked right into the data stream, block producers spend significantly less time arguing over the order of events and way more time actually packing blocks full of transactions. Let's see this in action on a timeline. At time 1, validator 1 receives transaction A and records it at POH index I. Then, at time 2, a completely different node, validator 2, receives transaction B and records it at POH index I plus 3. Because both of these transactions from different clients are effortlessly anchored to that continuous, unforgeable proof of history stream, the entire network instantly knows that transaction A came first. The sequence is mathematically built in. It's just effortless. And the grand result of all this? Proof of history enables massive parallelization. Look, saving validators from constantly bickering over milliseconds might sound like a minor architectural win, but it is exactly what allows the Solana network to process huge, overlapping batches of transactions at blazing speeds. Instead of waiting in a single-file line to check a global clock, everyone runs forward together, knowing the cryptographic stopwatch is keeping track perfectly. Okay, as we wrap up, let's summarize and really lock in the 3 core principles of proof of history that you need to take away from this explainer. 1. Proof of history creates an intrinsic, verifiable order using a continuous hash chain. 2. It is strictly complementary to consensus. It speeds things up dramatically, but it doesn't replace the final vote. And 3. It dramatically lowers the coordination cost across the network, opening the floodgates for incredibly high throughput. Next up in this track, we'll be diving into POH timestamping mechanics. We are going to unpack the actual under-the-hood data structures and the specific validation checks buried deep inside Solana's codebase. You definitely won't want to miss how these elegant metronome and film strip concepts translate into hardcore Rust code. But hey, before you go, I want to leave you with a final, slightly provocative thought. If time in a decentralized network is fundamentally just a verifiable sequence of hashes, what else in our digital world could we perfectly order without ever needing a physical clock? Think about the possibilities that unlocks. Thank you so much for joining me for this explainer on the Foundry by Forge College. To dive even deeper into this subject and explore a ton of other fascinating Web3 topics, make sure to visit forge.college. Keep building, keep learning, and I'll see you in the next explainer.